Okay, yeah, thank you. So, yeah, my name is Mario. I'm from Jülich Supercomputing Center. Actually, this work has been done by Shota Ito. He was, at the beginning of this year, he was my master student at RWTH Aachen University. Now he is a PhD student at KIT, and I'm here, but I just thought it's okay to show everything because it was actually his work. But we somehow used it and yeah, for another tool, which I will present now. I will go through these 5 steps during the talk. First of all, an introduction and motivation, then some numerical methods, 2 validation cases, then the real nasal airflow simulations, and a summary and an outlook. But before I go on with these, I would like to bring this idea of using wet surface modeling, or why we did this, bring this into a larger picture, because there comes also my role into play. I'm not the expert on these numerical methods that Shota developed, but I try my best to present it. So first of all, introduction, what is the human nose, or what does the nose do? We heard lots of interesting facts already and introductions in the previous talk. So I guess maybe I don't have to go through everything, but just to give you those that are not so familiar with the nasal cavity, yeah, a brief overview about the different parts or what's important in the nasal cavity flow. We have the septum, which is the wall that separates left and right nasal passages. You have middle and inferior turbinates which have been shown in the previous talk. Then we have the nostrils where the inlets are. We have, in our case, the outlet is at the pharynx, so we only compute until the throat, so to say. And yeah, several functions, conditioning, filtering, smell perceiving. But what's interesting is that the 80% of the alveolar conditions, so the conditions the lung can ideally work with, happen in this nasal cavity. So the rest, before the air goes deeper, in this for this case are only 20%, which is why it's a really important organ or part of the body. And this was only a general introduction. I worked the previous 5 years on these problems, which are septum deviations. So we have as a more general introduction that 2 or 4% of the population have polyps. These are quite frequent, but the most frequent, I would say, disease or pathology is the septum deviation. Maybe some of you also suffer from this. We can see this example here. So the septum is somehow tilted and the nasal passage is narrowed, and people complain about difficulties in breathing in and yeah, having quite difficult times. This is the situation. Another problem is from our perspective, but also from doctors who approached us. We worked together with the University Hospital in Aachen. They said, okay, when the patient come to our office or to the clinic, they can make a subjective perception, like a survey. They have CT images, smell tests, but when they perform surgery, they don't really know what they are doing. So they have no physical justification for where to remove tissue or where to not remove tissue. The satisfaction rate is only 50%, roughly 50%, which is our approach was to develop a tool where the doctors get yeah, like a surgery planning tool where they get physical justifications for their interventions. And this was the preliminary work before we started with Shota with the humidity transport. So this was mainly my work that I wanted to briefly show. So let's say a patient comes to the doctor, has a CT image. First, there is a super resolution network that yeah, increases the resolution of the CT image, because in order to perform highly resolved CFD simulations, we also need highly resolved CT data. And a drawback of most of the CT data that are captured in hospitals is that the resolution is too low, which is understandable because it's cheaper for the insurance companies, and also it imposes less radiation. So that we developed one tool to improve the resolution of CT images, make them feasible for highly resolved simulations. Then an automated step for the segmentation and for the surface extraction, and a surgery planning tool, which is back and forth between our lattice-Boltzmann solver, which has been developed in Aachen, the in-house code, and a reinforcement learning algorithm that explores different surface modifications and until the perfect modification is found with respect to, for example, pressure loss from the nostrils to the pharynx. We can see that before the surgery, the condition before the surgery had a pretty large pressure loss. And according to the surgery plan that has been proposed by the AI tool, reduces the pressure loss. This is just a brief summary. The doctors and also one patient who approached us mentioned that, okay, this is nice, but actually only pressure loss, looking at the pressure loss is not enough because many complaints, I mean, it might be sufficient for the septum deviation, but if we want to have a broader application for different types of pathologies, which I will come to later, we need more. And that's where this topic came into play. Okay, the student and Moritz also, whose name was on the slide, we thought, okay, let's try to implement or to include also humidity transport and temperature to have more physical quantities to really evaluate the situation of the patient and improve it. Because if we can see what we can see here, when we subdivide the nasal cavity into 3 parts, those 3 parts, this is from a study, which I also will show, or you can also see in the references later. Only in this very first part, location nostril to location 1, so this very first part, most of the humidification happens. So the difference in relative humidity that happens from here to here is 34%. Whereas those that happens in later parts of the nose are much less. So it is important to consider it. And therefore, we needed to think, okay, how do we numerically implement it? And we have this convection diffusion equation. We introduced the Peglet number and needed to solve 2 additional convection diffusion equations, one for the heat equation with the thermal diffusivity, and one for the humidity transport with the concentration coefficient. Okay, how was this realized numerically? So we use the lattice-Boltzmann code, as I mentioned before. These are the basic equations for the normal lattice-Boltzmann code. We have the particle distribution functions, the discretization models for 3 dimensions. I just showed this for to show the difference of these notations, but we use the 3-dimensional and 26 potential streaming directions. The lattice BGK equation, propagation and collision steps. And in the end, when we have, for each time step, we have computed the distributions, we use the statistic moments to compute the density or velocity fields, the macroscopic quantities. However, now when we think about the convection diffusion equations, we were thinking how to do this best. And we thought by introducing 2 more sets of particle distribution functions and also equilibrium distributions. So the phi is just a placeholder. So we had 2 of these sets to compute the temperature and the relative humidity. This is an example of our in-house code for the grid generation part. So here we see the head and the nasal cavity. The concept of the grid generator it's for Cartesian meshes. We start with a very large cell, 1 cell, and then we get smaller and smaller in this octree structure. So each parent cell has 8 child cells, and those that are outside of the SCL are just kicked out. And if this process is repeated by a predefined number of refinement steps, ultimately we reach to a resolution that is where we are satisfied with. And these are direct numerical simulations. So we have 200 million cells computed in Jülich on the supercomputer. And while this is still going on, I wanted to explain a bit about the boundary conditions. At the inflow, we have this well-known equation of Saint-Bernard and Wanzel. The velocities are extrapolated from the inner cells, ambient temperature and relative humidity of 35%. I don't know exactly where this value comes from, but it must be from a reference in the literature, which Shota knows. Then outflow, we reduce the pressure iteratively at the pharynx until a predefined volume flow rate is reached. And once this is reached, the iteration continues. So it goes back and forth, this value, with an iterative process that we implemented. For the velocity, temperature, and relative humidity is also extrapolated from the inner cell. The wall boundary condition, I will go a bit more into detail later, but for now it's a no-slip condition with the interpolated bounce back scheme. Then, okay, we now have our set of equations for the humidity and for temperature, so to say passive scalar transport equations. But this is not sufficient because, as we have heard in our previous talk, the mucus layer is also very important. And now I realize your figure was much better than mine, but it still shows, I guess, the main parts that lead to this mucus layer. For example, the production of the mucus in this nasal gland, or the nasal cilia, which are these fine hairs that make sure that particles are, so to say, guided in the right way. And then we have this very thin mucus layer, which is crucial for the humidity because we have lots of effects going on, latent heat effects, the production of the fluid, and so on. So that's why we thought about modeling the wall in this way. So we have the organ side, the mucus wall, and the nasal cavity. Two sets of fluxes. We have the water flux with two different concentration coefficients, one for the mucus layer and one for the fluid itself, and the same for the heat transport. The validations, so Shota used two cases to validate the model. One is the so-called Gaussian hill transport, where we look at the transport of species concentration after 200 time steps. We have the following initial condition, and we know the analytical solution. And when we compared two cases, one case that's more diffusion driven with a large diffusivity coefficient and very small convective velocity, and the other case the other way around. And we saw that the agreement is quite good. Same for the sinusoidal pipe flow, which is a periodic pipe flow with a uniform velocity field, which is mainly, this is the radius and this is the stream, the axis of the pipe. And we have incoming flow and this wall concentration imposed at the wall. And also a good agreement between the analytical solution and the solution by our solver. And after this, we came then to the flow simulations. The first thing I wanted to show is the latent heat effect. So we measured or we compared the different locations inside of the nasal cavity with and without the latent heat effect. As we know, the phase transformation in the nasal cavity cools down the mucus layer if the latent heat effect is considered, and this is what we also saw from our computation, that with latent heat on, the temperature at these spots, the average temperature is a bit lower, so the cooling effect is considered. And on the other hand, more fluid is transformed in the gas phase and higher humidity in the fluid. And this is comparison to a study from literature. It's not the same nasal cavity, that's why it doesn't match well. But we can see that the trend also, for example, the slopes are much probably better than if we consider the latent heat effect or not. But this is not a validation. This was just a comparison to another case that also used these effects. Then the last part of the story is that previously in the introduction, I was talking about septum deviations. So this was for my PhD from 2019 to this year, the patients that I dealt with, but then there was a new patient contacting us via email that she saw something from us in the online. She read something, and she would ask us if we could help her. And since we're not doctors, we were a bit skeptical, but we sat together and said, okay, how maybe we can help her. So she had this problem of very narrowed passages, nasal passages, and difficulties in breathing in. Then she went to the doctor, the surgery, and widened these passages. You can see that here. Her problem is now that when she breathes in, she has a very dry feeling at the back of her throat, difficult to show, but and this is really inconvenient and also painful if she breathes or when she sleeps. She wakes up and has strong pain in her throat. And we implemented the humidity model with Rüttgers' help and analyzed the flow. And first analysis is so this surgery is called turbinectomy. If you remove parts of the turbinates and widen the nasal passage. So this widening of the nasal passage was on the one hand for the total pressure an improvement, because after the surgery the pressure loss is much lower, which makes it easier to breathe in. So her initial complaints were gone. She could breathe in easier, but the humidity was the reverse. So it was after the surgery we have a lower humidity at the throat, which means drier air, and also it matches a bit with her complaints. These fluctuations come from the fact the way we collected the data. So this is the centerline approach, and in this centerline approach we made a spatial average for each point along the centerline, and sometimes these cross-sectional areas intersect, and then we have these fluctuations. But what's important is the difference before and after surgery. Then the final slide. What we can see here is, okay, that's what we could see before. The pressure loss has got reduced, but this spot is exactly where she feels the pain, and we can see that this is exactly the spot where the incoming air has a very low relative humidity. And when we showed her the results, she told us, yeah, this is exactly where she has the pain. So this is somehow where we could already at least show the problem. The surgery is in the past, so there's not much to do now, but at least we could help her to understand what's the problem. Okay, to summarize, so the lattice-Boltzmann method of our in-house code was extended to simulate relative humidity. We had 2 validation cases and could analyze at least the impact of this turbinectomy. The outlook now is to use this humidity transport model and implement this into this pipeline that I've showed before for this automated artificial intelligence-based surgery planning tool. This would be the next step. Okay. Thank you. And